Good morning and welcome to QI Lab's booth presentation for GeoConvention 2020. My name is Bill Goodway and I will be showcasing some of QI's quantitative interpretation technology used to characterize the lithologic controls on geomechanics and minimum effective horizontal stress for Montney unconventional oil. I would like to acknowledge my co-authors Dave Cho, Evan Mutual, David Miller, Lindsay Miller, and Dave McHarg, as well as their past and current work affiliations. As an introduction, I will start with a historical perspective on technology applied in reservoir characterization of the Montney. This started primarily with engineering requirements of understanding how easy it is to complete a well to frack the Montney, and this invoked concepts which have become familiar in unconventional applications now, such as brittleness, measurements of Poisson's ratio and Young's modulus, to try and define some criteria for failure. From that, the applications went to more of a seismic basis that included some structural attributes like post-stack attributes, some anisotropy, all in the goal to understand increased perm or increased natural fractures. More recently, quantitative interpretation has entered the picture in terms of trying to do some rock physics inversion for porosity and mineralogy and hence identify sweet spots. And this talk will now concentrate on something that's even more recent than quantitative interpretation applications, and that is to try and understand from seismic, from quantitative interpretation, aspects of stress characterization such as pore pressure and frac gradient back to the geomechanical requirements for the hydrofracking. So let's go back now and understand where we came from in terms of unconventional play motivation for things like quantitative interpretation, LMR, lithology, moduli, etc. The top portion of this slide shows the concept of brittleness. This is basically a cross plot of all the shale plays in North America, or a number of the shale plays in North America, including the Montney shown in this green outline. And you notice this distinct trend to the origin. Now, one aspect of this origin is that on the x-axis is Poisson's ratio, which has low values, but on the y-axis, the Young's modulus component of this brittleness index is reversed, so that it's increasing to higher values downwards on the y-axis. So what this basically produced was an idea of brittleness, given here in two measurements from McKeon and Rickman, by trying to come up with a fractional change in, say, Young's modulus and Poisson's ratio, and then averaging those fractional changes. And the trend is basically lower Poisson's ratio with higher Young's modulus. Despite that relationship, you can see that there's a cross trend. And one other noticeable thing about the cross plot is that I show here a conventional clastic kind of points for sand and clay, or clay mixture. What's missing from this brittleness plot is a concept of porosity. And here are lines of porosity, or different mineral mixes going from quartz to clay, clay to limestone, and limestone to clay and clay to limestone. And you can see that in terms of porosity, for the quartz-dominated rock, it's going in that direction. For the shale-dominated rock, it's going in pretty much a constant Poisson's ratio direction, and limestone is increasing in this direction. These are lines of increasing porosity, and they're basically perpendicular to the brittleness trend. Another thing notice about these porosity trends, depending on the mineral mix, is that in some cases Poisson's ratio increases with increasing porosity, and in others it decreases, while for the shale it's basically staying constant. But in all cases for porosity increase, there's a reduction in Young's modulus, which is not the basic direction that brittleness would try to predict for better completions. The slide at the bottom portion shows a mineralogical perspective of the brittleness. It just shows a fraction of quartz and dolomite divided by quartz, dolomite, limestone, clay, and TOC. So that's another mineralogical measurement of brittleness. Okay, back in the early 2000s, there was this publication from Grigg at an SPE meeting, and this is basically where this concept of linking Young's modulus and Poisson's ratio came for the engineering world. And you can see from this cross plot, there's a distinct trend for the Barnett for increasing Young's modulus and decreasing Poisson's ratio. This is basically an empirical trend, and Grigg has a fit here. There's a linear fit to that trend. However, you look at the mathematical relationships between Young's modulus and Poisson's ratio, you can see that increasing Young's modulus, decreasing Poisson's ratio in the denominator of this ratio is just basically an increase in mu, the shear modulus. So far we've considered three moduli that can be combined into, or two moduli that can be combined into one. And the next question would be, what about the missing modulus, such as things we're familiar with, such as the bulk modulus, kappa, or lambda? And in this situation, these mathematical relationships are a little more ambiguous. For a decrease in Poisson's ratio and an increase in Young's modulus might imply a decrease in incompressibility modulus K, or might not. So in order to try and understand where these particular moduli, which are more to do with bulk properties such as porosity and fluid fill, you can combine all the moduli into one cross plot and see how the Grigg trend, this empirical trend, fits. So here we have a lambda versus mu cross plot, and the curved lines are lines of constant Young's modulus decreasing to the origin. The sloping lines are constant p-wave modulus, again decreasing to the origin, and radial lines are Poisson's ratio going from low to high. And finally there's the Grigg trend. This is the whole empirical trend, and you can see it actually curves. And for the lower portions of that trend, there's a ductile range which I've defined as basically constant high Poisson's ratio, and then the brittle range, which is up in the top left quadrant of the lambda mu cross plot, which is where you would expect quartz as a lithology to reside. And so that makes sense that the brittle trend is basically going from a shale, ductile shale, to a brittle quartz-rich component of the clay, or even to quartz. And this is also captured now for the bulk modulus. This is a plot of Young's modulus versus Poisson's ratio with radial lines of increasing bulk modulus. And these dotted lines, as on the previous slide, are for various mineral mixtures with porosity going to the lower Young's modulus in all cases of the mineral mixes. And again, you can see that these increasing porosity lines are perpendicular to the radial lines of increasing bulk modulus. In other words, they go in the same direction as the bulk modulus, which is what we might expect. If I flip the axes there to compare to the Young's modulus Poisson's ratio Grigg empirical relationship, you can see that in general all the porosity trends are opposed to that increasing Young's modulus with decreasing Poisson's ratio trend as predicted by Grigg for the Barnett. So it begs the question, how much was missed from this empirical trend due to not having a concept of porosity through the bulk modulus or lambda and pore fluid fill? And the reason that might be important is that the porosity parameter in the rock might be indicative of some natural permeability. And that just confirms this direction for the porosity increase on the lambda mu cross plot, which is perpendicular to the Grigg trend. Okay, just quickly looking at some moduli now that we might be expected to gain from quantitative interpretation. Here is a cross plot as a template for lambda rho versus mu rho. The trend here, this vertical trend, is porosity increasing to the origin. The curves again are Young's modulus. which are increasing with higher mu. So in fact, higher rigidity, higher shear modulus implies a higher Young's modulus. The Poisson's ratio decreases in that direction, in the curved direction, from what was previously a linear radial lines. Notice that the Poisson decreasing direction, which is sort of quite diagnostic of going from clay to quartz, you can see that that is actually also the increasing error direction in most quantitative interpretation. And finally, at the bottom is an increasing or direction from this yellow arrow for decreasing lambda rho as indicative of increasing OCHIP, TOC, pore pressure, porosity. And finally, on this cross plot are actual seismic based points derived from a 3D quantitative interpretation at particular well locations where we had measurements of EUR per frac. So you can see the EUR per frac increases in that horizontal lambda rho direction, and the breakdown pressures, which are decreasing, low breakdown pressures with decreasing Young's modulus, which is again something you might expect from a porosity component of the unconventional rock. So what do we mean by brittle failure? Well, brittle failure basically is a concept for high shear modulus, low lambda rho, and that is something that is a rock, it defines a rock with a low closure stress ratio. And by that what I mean is that, we'll see in the next slide, this closure stress ratio defines the amount of lateral strain or lateral convergence of vertical stress or stress in one direction to the stress in the other direction. So it's a ratio that those two stresses. We might consider that minimum horizontal stress versus vertical stress, which we'll look at later. And because that ratio is low, it means that the material doesn't expand or doesn't transfer the stress, and so it tends to take the stress up in its matrix and eventually cracks under the higher load. By contrast, a ductile plastic deformation bends quite easily in ductile kind of flow. It expands quite readily, and there isn't much transference of there is a large transference of the stress horizontally from a vertical overburden. And here is that closure stress ratio. It's just lambda over lambda plus 2 mu, so it has similar properties to Poisson's ratio. So decrease in lambda decreases the closure stress ratio. And finally, you can plot brittleness on the lambda rho mu rho cross plot as decreasing brittleness towards the origin with increasing porosity. So let's just look at this horizontal closure stress equation, again from engineering literature. This equation is basically a bound equation, so it defines the minimum horizontal closure stress to open an existing fracture plane given in this schematic. So on the left-hand side of the equation is the effective minimum horizontal stress, which we'll look at in more detail. On the right-hand side, there is this overburden stress. So the vertical stress from the overburden minus the pore pressure times the BO coefficient multiplied by this ratio of Poisson's ratios. And the last term here is a tectonic term, which interestingly is a function of Young's modulus divided by negative Poisson's ratio squared. And so you can see immediately that higher Young's moduli would create a higher horizontal closure stress. And then there are some strain terms. You can convert that equation directly to lambdas and mu's and LMR. And here we see that the ratio of Poisson's ratios is simply the lambda over lambda plus 2 mu ratio, the closure stress multiplier. And it multiplies into the effective overburden stress plus this tectonic term, which is a function of the horizontal maximum stress and the aspect ratio of that elliptical fracture. This tectonic stress is something that is rarely considered in any, certainly not in any quantitative interpretation, and that's something which at QI Labs we are progressing with in terms of anisotropic measurements and anisotropic quantitative interpretation, but will not be covered in this presentation. You can rearrange that equation. You can plot that equation on a cross plot of overburden versus minimum closure, and you get these slopes which are a function of that lambda over lambda plus 2 mu closure stress ratio, and the increasing pore pressure which creates the fracture or opens the fracture increases to the origin. So you might see a good completion, this fairly gentle slope towards the origin, and a poor completion on a steeper slope again towards the origin. So an outline of my talk: we'll start with an effective stress overview, look at the Beer-Willis coefficient and the effects of porosity and mineralogy on the coefficient, and then we'll look at the modeling case study where we went through the rock physics modeling and inversion. We estimated a Beer-Willis coefficient, came up with a pore pressure prediction from Bauer's method, Eaton-Bauer's method, and then combined all that into predicting the fracture gradient or the minimum horizontal effective stress. So what do we mean by effective stress? Well, the definition of effective stress is the proportion of the external load to total stress carried by the rock itself. And you can see here it's basically the stress of confining stress in the rock minus the Beer coefficient times the pore pressure. It has applications in drilling and hydraulic fracturing because increasing the pore pressure is the way that we shift the more circle towards the failure envelope to cause failure. Again, this is normal stresses versus shear stresses on the more cross plot. The definition of the Beer-Willis coefficient is that the Beer-Willis coefficient represents a portion of fluid pressure which will produce the same strains as a total stress. The Beer-Willis coefficient represents a portion of fluid pressure that counteracts the confining stress, which is what I mentioned in the previous slide. And the mathematical definition is just basically 1 minus the drained bulk modulus divided by the solid phase bulk modulus. And that can be rearranged or rewritten in terms of lambdas and mu's. And on the right hand side of this equation you can see it's a difference between the solid lambda minus the drain lambda plus the solid shear modulus mu minus the drain modulus mu. And so only the drained lambda actually responds to the pore space fluid compressibility, which is what the Beer coefficient is defining. Whereas the drained bulk modulus refers to deformation in which a pore pressure remains constant. So let's look at the porosity effects on the Beer coefficient. We'll look at limiting cases from the lower bound zero porosity and upper bound critical porosity. Here is the same effective stress equation and the Beer coefficient. And for the total rock porosity, you can see the numerator here, the drained bulk modulus, is what is being measured because this is containing the total whole rock porosity, which is drained. Whereas the solid bulk modulus is just basically the solid you might for the rock in one of these grains, as if the rock had no porosity. So the lower bound at zero porosity means the rock frame and the solid phase are the same, and that means that drained is equal to solid, and so the Beer coefficient is 0. For the upper bound, you can see this occurs at critical porosity. The grains are now in suspension, so it's infinitely compressible. The drained bulk modulus is 0, and so the Beer coefficient is 1. So what does this mean for different types of minerals? For clay with a low bulk modulus, has a high Beer-Willis coefficient, and for quartz with a high bulk modulus, it has a low Beer-Willis coefficient. And the way to see this is that if you apply this confining stress to some porous material, then the resisting pore pressure stress is given in terms of a high Beer-Willis coefficient for the pore pressure contribution to the effective stress for clay, and a low Beer-Willis coefficient for the contribution with respect to quartz, because the quartz matrix, which is stiffer, is taking up more of the confinement and resisting the confining stress. So now let's look at the effective stress estimation. So we have, as I showed before, the lithostatic vertical loading term. We have the pore pressure term, which we just discussed with the Beer-Willis coefficient, and we have a tectonic term, all combining to produce the effective horizontal minimum stress. From the point of view of the effective stress, we can look at the same equation but without the tectonic term. So that's what I'll be considering in the next few slides. We can investigate the effective stress response to failed rock under the following conditions: uniaxial strain, which is what defines this bound relationship, and constant pore pressure. So for high quartz and low clay, the low Poisson's ratio means a larger deviatoric stress, that's a larger deviatoric stress here, and a high friction angle on the failure envelope. For low clay, with low Beer-Willis coefficient and higher pore pressure for failure. So what that means is that we need more higher pore pressure to get to the envelope, failure envelope, shown by that direction. For the low quartz high clay case, we have a high Poisson's ratio, so a smaller deviatoric stress and low friction angle, and the high clay low Beer-Willis coefficient means a lower pore pressure for failure. And notice that the slope friction angle is actually again a function of Poisson's ratio. So the lower the Poisson's ratio, the higher the slope angle for things for more quartz-rich rock. Okay, so how can we estimate these parameters from quantitative interpretation? Well, looking at rock physics modeling, we can model relationships between elastic and petrophysical parameters using a regression-based model, which is quite common. This connects the elastic moduli to porosity, mineral fractions, and fluid saturations. And so we can capture all these local trends as long as we know we can regress and fit the mineral end member moduli. And this allows us estimation of mineral fractions, fluid saturations, bulk moduli, and shear moduli. This shows the modeled bulk modulus. So we've got the observed against the model, and you can see that the rock physics trends have captured that quite well for the Montney, showing all these different zones within the Montney. So there's quite a large high correlation coefficient for all this modeling for the bulk modulus and the shear modulus. In terms of the model lines, you can see the model lines that have been created by the rock physics model in an AI VPVS crossplot. So here at the top pair of panels are the model lines, and the bottom panels show the actual log data with overlays of total porosity and volume of clay. So you can see there's a good correlation, good calibration of the model to the actual log data. So from that, we can run the AVO inversion, and this gives us basically the AI, VPVS, and rho. And here we've run the AVO inversion for elastic parameters and got a good fit to the actual filtered log. So we're quite confident that the data is responding and we're getting some meaningful results. From that, we can run a rock physics inversion due to the model, rock physics models, and instead of the elastic parameters, we get porosity, volume of clay, and volume of dolomite. And again, within the zone, you can see that this is actually a good fit to the actual filtered log data for these petrophysical rock physics measurements, which are necessary for trying to compute the effective minimum horizontal stress. This is a set of horizon slices, again for porosity, volume of clay, volume of quartz and limestone, overlaid by some microseismic, and you can see that microseismic is concentrated in these higher porosity zones, as well as in the higher quartz zone areas. And so this gives us some confidence that we are, between the porosity and the quartz estimate, coming up with meaningful measurements or distributions and mapping of the minimal horizontal stress because of these microseismic events which have occurred in areas with lower minimum horizontal stress. The Beer-Willis estimation comes from the rock modeling and inversion. The gives us mineral fractions, mineral end moduli. This allows us to reconstruct the different components of the rock mass, and hence we can come up with the drained bulk modulus, the solid bulk modulus, and the rock physics model from the rock physics model. Here is the rock frame, and here is the solid. The pore pressure prediction, we can come up now with the seismic velocities based on high density horizon constrained picks and using Swan residual move out with logically consistent velocity model. And then we can put that into Eden-Bowers method, choose a normal compaction trend to reflect the onset of unloading, approximately Vmax in Bowers, and zone its specific Eden exponent. So the results of the Eden exponent of approximately 1 are shown here with the processing velocities, and then here with the Swan velocities. And you can see some improvement in detail in terms of the Swan residual move out velocities, matching the log values, the p velocity log values. So here are the processing velocities in cross section for the Montney zone, the Swan velocities with the detail for each individual Montney zone, and using Eaton's method with an exponent upper value of, for the upper Montney of 1.45, and middle 1.25, and turbidite 0.91, and the V normalized intercept of 3100 meters per second and a gradient of 0.962 meters per second per meter, we get a pretty good match between the predicted pressure and the observed pressures. And here's just another representation of that. Here is point measurements in the logs in the well calibrated data, and you can see for the pore pressure there's an increase in these mid-Montney, lower Montney zones that's captured by the pore pressure measurement from the seismic, and here's the fracture gradient that shows the effective stress, and that's just the vertical stress limit. So here's the final result of the pore pressure, the Beer-Willis coefficient from the inversion, and the lithostatic loading stress from integrating the density. And here is the effective stress by combining all those components in that minimum closure stress equation. So in conclusion, the Beer-Willis coefficient has both porosity and mineral moduli contributions and is lithologically dependent. The pore pressure can be estimated using conditioned seismic velocities and Swan velocities. Put some detail. The effective stress can then be computed with a combination of elastic properties, petrophysical properties, and the pore pressure with the BO coefficient. The pore pressure and fracture gradient volumes have direct use in drilling and completions design. And I'd like to acknowledge Progress Energy, now Petronas, Mark Norton, and Earth Signal Processing.